Hello everyone. Today we are going to discuss about the fundamentals of group theory. However, I must say that this presentation is for a beginner and it will be more inclined to the likes of a physics student. Therefore, the concepts presented here may not be of much use to advanced learners of group theory and to mathematicians. And before we begin our discussions on group theory, it is very important for us to understand why a physicist should learn group theory. And for this, we have to understand between group theory and symmetry. Symmetry is one of the most beautiful themes which unifies many areas of mathematics. But if mathematicians are more interested in the symmetry of shapes, sets, and matrices, we physicists are more interested in the symmetry of physical systems. So the study of symmetry, therefore, is of utmost importance in both in physics and in. Okay, so we will start with the a layman's perception of symmetry. And if you carefully notice this figure, what you see there is a drawing of a tree. One is symmetric about this plane and the other is asymmetric. What I mean by this is, see, if I place a mirror here, the reflection shown in the mirror will be the same as this side. And if I place a mirror here, the reflection in the mirror of this side will be different from this side. So it has no symmetry along this line. So as I said, whenever we talk about symmetry, a layman, a common man, will try to connect it with certain shapes or patterns. And he will find this tree symmetric, while he will not find this symmetric. He will find this asymmetric. Okay. Now, we can see a lot of symmetric elements in the nature itself. In fact, in nature, we often see more symmetric elements than asymmetric one. Look at these leaves. Here, they have some symmetric planes of reflection, and they're symmetric about this side and this side, right? So, and now, if you look at a butterfly, you will see even better examples of symmetry. When I stand here and look at both sides, what I see is a perfectly symmetric pattern on both sides. You can look yourself in the mirror to enjoy the beauty of symmetry, because you yourself have a lot of symmetries. And in fact, this sense of symmetry, sense of beauty that we have, it is connected to symmetry itself. See, if you look here, you have two faces, and which face will appear attractive to you? You will definitely choose this one, I'm sure, because this is highly asymmetric, and our this obsession that we have for symmetry may have its roots from our perception of nature itself, because of the symmetric elements that we see all around us. So yes, so now these symmetries of objects, it did not go unnoticed by our ancient philosophers and scientists. In fact, they were fascinated by the way in which objects in nature exhibited symmetry, and they believed that this would be mirrored somehow in the structure of the cosmos itself. And one of the most noticeable use of the idea of symmetry in physics can be seen in the works of the 17th century astronomer Johannes Kepler. And he was really wondering why the snowflakes have such a high degree of symmetry, such a high symmetric structure. What you see here is a close-up of the ice crystal being formed, and you can see that it is very, very highly symmetric. I mean, even since this still remains, completely unexplained. I mean, there is not a proper, 100% explanation to this behavior, this kind of a formation of ice crystal. At that time, to explain this, he developed, or he proposed, what is now called the morphogenic field, in which the system want to have the form they have. However, not so surprisingly, this was rejected by science. And although this has nothing to do with what we are learning here, I would like to add that ironically, this morphogenic theory of Kepler was resurrected by some scientists to explain how spiral galaxies preserve their symmetry as an alternative. This is a spiral galaxy, Messier 81, and yes, now symmetry in physics is not just restricted to shape of objects. In fact, symmetry in physics is when a physical law is unchanged by transformation in one or more coordinates. In that sense, the Newtonian mechanics embodied the symmetry principles. This is pertaining to the principle of equivalence of inertial frames, or what is popularly called the Galilean invariance. And we know that these symmetries involved in Newtonian mechanics, they led to conservation laws. Okay, nevertheless, the advances made by Albert Einstein in 1905 by introducing the theory of relativity underlined the need to put the principles of symmetry as a primary feature of nature, which controls the dynamical laws. Einstein's idea of relativistic invariance and the way he connected Maxwell's equation to the symmetry of space-time itself triggered a paradigm shift in the concept of symmetry in physics. With the development of quantum mechanics, new concepts of angular momentum, spin, etc. made symmetry to play a very important, a very fundamental role in physics. Now we will see an example of symmetries leading to conservation laws. We have been talking about that. How symmetries of Newtonian mechanics led to conservation laws. Now we will see an example where we have a particle of mass m moving under the influence of a central mass capital M located at origin here. Okay, the whole scenario looks like this, and if you assume the gravitational potential is spherically symmetric, no matter how you move the point mass around the center like this, the problem will be the same if the potential is spherically symmetric. So since the potential is spherically symmetric, it depends only on the radial distance between the origin and the mass. Okay, now let's go to the mathematical part now. Now, what is the linear momentum? It will be P equals mv, where v is the velocity of the mass m, and the angular momentum of the particle which moves around the origin, angular momentum of the particle will be L equals to r cross p, and with a few mathematics we will reach here, and here v cross v will be definitely 0 because both of them are parallel. We know velocity in the direction, sine theta will be here, VV sine theta, and theta will be 0, so this whole quantity will be 0. And what is left here is R cross M dV by dt, or R cross F, where F is the force on the particle. But if you are assuming a spherically symmetric potential and your force is a central force like gravitation, then definitely F, the force acting on the particle, should be parallel to R. So definitely then if your dl by dt, which is this, your dl by dt, that will be 0, because this quantity will also become 0 since they are parallel. Okay, in that case you can say that since dl by dt is 0, L is a constant, you have to integrate both sides. So or in other words, you can say that the angular momentum is a conserved quantity in the presence of spherically symmetric potential. Thus, it is obvious that the symmetries lead to conserved quantities and therefore conservation laws. All conservation laws, including conservation of energy and momentum, find their origin in underlying symmetries in nature. Or in other words, we can say that nature reveals herself to us using the language of symmetries. Alright, so now we will see how symmetry is, how deeply it is connected to the cosmos. If you look at a molecule, you will see there is a lot of symmetric planes, and there is a lot of reflection symmetries and rotational symmetries for a molecule. There are, and if you look at this molecule, which is of molybdenum hexacarbonyl, which has got an octahedral geometry, if you look along this plane, then you will see a symmetric distribution in both directions, the distribution of atoms. And if you are here, you're lying down here, you can see a symmetric distribution again. So there are many planes in which this symmetry can be observed. So this kind of a nature of molecule can be vital in its studying its rotational, vibrational characteristics. Also, if you look here, this is the lattice, hexagonal lattice of graphene, and it has got a honeycomb structure. And if you look here, this hexagonal lattice has got, the symmetry is very evident here, with this highly symmetric distribution of the hexagonal graphene. And and by the 20th century, the link between symmetry and the laws of nature became more evident. In cosmology, symmetry is the door to the mysterious or the unknown, and the standard model of the universe defines three near symmetries: the C symmetry, the P symmetry, and the T symmetry, which were all combined to form a highly symmetric state before the Big Bang. And after the Big Bang, these symmetries were broken and the present day universe is formed. And today what we believe is that this symmetry could be the door to a unified theory. And from our earlier discussions, we know that the nature unfolds herself before us in the language of symmetry, and just because of that, the door to the unknown is, or the key to the unknown is, understanding the symmetry of the cosmos. And despite of all these complications, symmetry, the definition of symmetry could be as simple as it can be defined as a property of an object which remains invariant under some operations. Now, having discussed all the significance of symmetries in physics, the next question we have to answer would be, what is the connection between group theory and symmetries? For a physicist, group theory is the mathematical structure which underlies the study of symmetries, and it can also be defined as a complete set of symmetry operations. This is a physicist definition. Symmetry, a complete set of symmetry operations can constitute a group. And now we have to understand what symmetry operations, set of symmetry operations are. I will give you a simple example. Suppose you have a square like this, ABCD, whose corners I have labeled A, B, C, D, and if you rotate it by 90 degree, you will get a configuration similar to this, but with the labels changed, right? Without labels, you won't be able to understand whether the square has retained its initial configuration, that of A, B, C, D. Then again, 3 more rotations will lead the square to regain what it was initially. It will become ABCD eventually. And see, for a square, this is not the only rotation is not the only symmetry operation. There is reflection symmetry, of which we will have to study this very in an elaborate manner later. But this is just an example to understand what symmetry operations are, and the combinations of these symmetry operations can together form a group. Okay. Now we are now about to discuss very important. We are switching to the mathematical framework of group theory.